Hello, welcome to the pre-class video assignment for section 1.8. This one is going to be about something called exact equations. So again, this is referring to a specific type of DE that we shall identify a little bit later on in the section. But suffice it to say for now that exact equations are derived from and ultimately often end up with giving us implicit solutions to differential equations instead of explicit solutions that we are mostly accustomed to. So just a quick reminder on what that means here. The word explicit function, or the term explicit function, is referring to a function that is solved for the output variable, so typically y. So this would be an explicit function for y equals f of x. And of course, the significance then is that there are no y's on the right-hand side anymore. This would be explicit. In an implicit relation, again, in an implicit relation need not be a function at all, but in an implicit relation, we really just have some sort of expression involving x's and y's equals 0, because everything could be brought onto the left-hand side and set equal to 0, but we have some situation where these are all combined together. So not solved for y, basically. Not solved for the output variable. So here's a simple example just to illustrate. If you think about the top half of a unit circle, the top half of a unit circle is indeed a function. It passes the vertical line test, and we can write a function notation for it. The top half of a unit circle, well, in either case, a unit circle is x squared plus y squared equals 1. You can solve this for y and get y equals the positive square root of 1 minus x squared. This would be the top half of the circle. So this is explicit, and this is a function, and this is all good. Yes. An implicit relation here would be the equation of the unit circle, x squared plus y squared equals 1. This is not solved for y, or for x for that matter, but it's not solved for y, so this is implicit. When we look at this equation implicitly, notice that this is not even a function at all. So this is an implicit relation because it fails the vertical line test, right? A vertical line intersects this curve more than once. So again, this one would be implicit. Sometimes implicit relations can be solved for y, and sometimes they can't. Certainly this one can be solved for y. You can solve it and get y equals plus or minus the square root of 1 minus x squared. Notice that, of course, this is then showing us that this implicit relation is really just two explicit functions pasted together. One is the top half of the circle, the other is the bottom half of the circle. And if you paste them together, you get the relation x squared plus y squared equals 1. So you can consider in this case having an implicit relationship that is basically just two explicit functions pasted together. So it turns out that we can have solutions to DEs that are indeed implicit. Again, we've already been seeing explicit solutions, but you can certainly also have implicit solutions to differential equations. So here's a fairly simple example to solve. This one is verify that this implicit relationship, x plus 2 equals y squared, is an implicit solution to this DE. All right, so this is not terribly difficult, and maybe not surprisingly. In order to determine this, or to judge this, we take our implicit relationship and we need to differentiate it implicitly. So differentiating implicitly is something you learned in Calc 1, so you want to remind yourself about that here. But it basically comes out as follows. You basically are differentiating both sides of our implicit relationship with respect to x. On the left-hand side, we get the result. The derivative with respect to x of x plus 2 is just 1, right? The derivative of x is 1. The derivative of 2 is 0. The derivative with respect to x of y squared Now, in this case, we have to remember that in theory, y is a function of x. So we have to actually apply a chain rule here. The derivative with respect to x of y squared is the 2 comes down in front, we get a 2y to the power of 1, and then you have to multiply by the derivative of the inside. The derivative of y we call dy dx. So this is what we get by implicit differentiation. If you solve this for dy dx, we fairly immediately verify that indeed this implicit relationship results in the correct differential equation. You can think of it as getting this result and then taking this result and substituting 1 over 2y on the left-hand side, and then we trivially get an identity here. So this is a solution. So that's actually pretty easy for this one. Probably a little trickier and worth mentioning here is the interval of definition here. If this is indeed a solution, notice that this is implicit and is not even a function. Again, you can solve this for y. If we solve this for y, we get y equals plus or minus the square root of x plus 2. This ends up being, this is plus the square root of x plus 2, and this is minus the square root of x plus 2. So we get, again, these two explicit functions. When you paste them together, you get the implicit relation. But realize, remember what we've said about intervals of definition. They cannot contain a place where we have no derivative. So clearly on this function at the vertex here at x equals minus 2, we have a vertical tangent. Therefore, there is no derivative there. So in theory, we have a solution here, but we already have two of them. I could either take this guy as my solution if y is positive, or I can take this guy as my solution if y is negative. So we cannot have this whole thing exists as a single solution curve at once. It has to be one part or the other. And again, this is generally determined if you have an initial value problem and the y coordinate is positive, you would use this one. If you have an initial condition and the y coordinate was negative, you would use this one. All right, so the first up then is a few examples to try on my open math. This is not differential equations. It is just practicing implicit differentiation from Calc 1. So to remind yourself about that. Okay, so next up then, in exact equations, there is a particular form of DE that lends itself to being solved by the method, and this is something we call differential form. I do believe we mentioned it briefly previously, but this is where it really shows up, the differential form of a DE. So just as an example here, or just the definition, normal form, we remember, first order normal form is where we have the DE solved for the first derivative. A second order in normal form would be where we have the DE solved for the second order derivative, and so on. In differential form, you basically take something that was first order and we basically split it up and write it in this fashion. So it's m of xy dx plus n of xy dy equals 0. So that basically means we have some sort of expression involving x and y dx, another sort of expression involving x and y times dy equals 0. So we can always switch between normal for first order normal form and differential form. We can always switch one of these to the other one because basically here, as you can see, if we take differential form, if you divide everything first by dx to get your dy over dx, and then you subtract m of xy from both sides, and then divide n of xy on both sides, you can convert something that is in differential form into something that is normal form. So we can always switch between these two forms. Again, but for the purposes of this section, we are interested in this differential form. Here's a quick little example. Here is a DE. kind of in no particular form. 2y prime minus y squared e to the x equals -25. The goal is to write it both in normal form and in differential form. Again, normal form is pretty easy. Normal form is just solve it for the y prime. So solving this for the y prime, we would just add this term to the other side, then divide by 2, and we have our normal form. For differential form, it's probably convenient to do the following. That is, the first thing we do is replace y prime by Leibniz notation, dy dx. And then we can think about breaking those apart into their differentials, dy and dx. So we can take this equation here and multiply both sides by dx to get this. And then to make a differential form out of it, we would want to subtract this whole thing from both sides. Notice, to subtract it, I can basically just change the signs of the things on the inside here and flip them around and then write them on the other side. And then we have our differential form. This would be the m, and this would be the n, and this would be our differential form. So that's where we're going to leave it here for those notes. We will finish this packet in class together. I also want to talk a little bit about some prerequisites for this section. So here we go. For prerequisites in this section, we again will need to understand something about partial derivatives. So we have previously, in a previous section, we talked about partial derivatives specifically with respect to y, like this. So we talked about this notation. This is basically the Leibniz notation for partial derivatives. Del y of f of xy. We would also write del f del y. There is also another much more convenient notation where we simply write f sub y, f subscript y. So this little notation here is nice and succinct, and it just means the partial derivative of f with respect to y. We might even write this as being basically equal to f of y of xy. So it is the partial derivative of the function. And again, the function f sub y could also be a function of x and y. We mainly looked at and needed previously partial derivatives with respect to y, but of course, the partial derivative with respect to x also exists, and we will need both of them in this section. We will need to consider both f sub y and f sub x. And again, this is the partial derivative with respect to x. We can even extend this notation to second derivatives and further, but we will go through second derivatives here. So we will have things like these, where f sub xx means you take the function x and then you first partially differentiate with respect to x and you get a result, and then you take that result and you partially differentiate it with respect to x again, and this would be f sub xx. But you can also do things like f sub xy, f sub yy, f sub yx. So the order matters here, yes. They are not necessarily the same, at least from what we've talked about so far. So something like f sub xy says first differentiate with respect to f and then with respect to x. So a couple of examples. Try, first of all, just a first order derivative, partial derivative on my open math, just to remind yourselves. Then let's take a little look-see. Let's do a little example here. If we look at an example like this, let's try one down here. So for example, if we have the function f of xy equals 2x squared plus 6 sine y plus y e to the x. Again, let's think about what those partial derivatives would be. So on the one hand, we can think about what is f sub x. So what was the partial derivative of this with respect to x? So go through this term by term. The derivative with respect to x of 2x squared would be 4x. What is the partial derivative of 6 sine y with respect to x? Well, with respect to x, 6 sine y is a constant, so that is just a 0. And then we have, I'm sorry, not e to the x. This is supposed to be a y e to the x. So for the last one, we have a derivative with respect to x of y e to the x. And in that case, the y is acting just like a constant. So what's the derivative of a constant times e to the x? It is the constant times e to the x. So this would be f sub x. It would basically be 4x plus y e to the x. And so from there, we can think about, well, what then is f sub xy? So what if we take that and then partially differentiate with respect to y? So now we're looking at this function and saying, how do we differentiate with respect to y? 4x doesn't have any y's in it. This is effectively a constant, so that becomes 0. And then the derivative of y, e to the x, is going to be just e to the x, right? If a derivative of a constant times y with respect to y is the constant, in this case, e to the x. So that is our f of xy. All right, so let's look at the others here. We can also think about a first order partial derivative f sub y. If I do a partial derivative with respect to y, then in that case, the 2x squared is a constant, so that is a 0. And then the derivative of 6 sine y, well, that will just be 6 cosine y. And then the partial derivative of y e to the x with respect to y, that is just e to the x. So this is what we get for our f sub y. It is just 6 cosine y plus e to the x. And then we can look at its second partial. This is, f sub y and then x. So what happens if we now take this function and attempt to differentiate it with respect to x? Well, with respect to x, 6 cosine y is a constant, so that is 0, and the derivative of e to the x is e to the x. So this is what we get. This is basically our, we would call these our mixed partials. The mixed partials, f of x sub y and f of y sub x. These are something we call the mixed partials. And what you might notice here is that our mixed partials are actually equal to each other. And this is actually not an accident. So if I may go back up here a little bit. There is a theorem here called Clairaut's theorem. Clairaut's theorem is that for any function f of x sub y, the mixed second partials will be equal. That is, f sub xy is equal to f sub yx. So that should always be the case. Next up, I'm going to try some examples here. Try finding some second partials in this next example. All right, so again, we then are going to have use of this theorem, Clairaut's theorem. Clairaut's theorem leads us to something kind of important, if though not difficult, in this section. So here is a little question about Clairaut's theorem. Give that a go. Okay, and then we have, let's see, we do have a couple of examples that we need for your prerequisites for this section, just for practice. So there is a slightly more tricky partial derivative to do. So try that on my open math. And then we're also going to need to talk about partial integration. We have been talking about partial derivatives. Partial integration is basically just the opposite process. So here is a fairly simple example in the notes here. If you are taking the integral of the function x times y with respect to y, we are trying to, this is like a partial integral. We don't write this, but I do think it would be kind of nice that had we written this as x, y, and then we could write del y to indicate a partial integral with respect to y. This is actually not normal notation, but I think it would have been good notation, but it is not written that way. We just write this, but again, it should still be clear. Partial integral of xy with respect to y. So treat x like a constant and integrate. So if you're integrating y, the constant just sits in front. So the x just sits in front. When you integrate y, you would have a y squared and a 1/2 in front. And again, when we integrate, there is a constant of integration generated. So the integral of xy with respect to y is a 1/2 xy squared plus a constant, which we have a little bit more to say about. Here's another little example. What is the antiderivative, the integral of y x squared plus 2 dx this time? So now we're integrating with respect to x. So again, the y is just a constant here, so just let it sit in front. What happens when you integrate x squared? You get a 1/3 x cubed. So overall here, with that first term becomes a 1/3 y x cubed. When you integrate 2, it would just be a 2x. And once again, in general, there is a constant generated. Now, note that these so-called constants are a little different than before. So note that when we are integrating with respect to y, what is considered a constant? Well, any function of x or any constant or any function of x is considered a constant. So C1 would have disappeared if it had been a constant or if it had been any function of x at all. So this is probably not general enough. Just call this C1. This is not general enough just to call it C2. This one here, because we integrated with respect to y, C1 could actually have been a function of x, and C2 over here, because we integrated with respect to x, C2 could have been any function of x, any function of y. So it is probably more accurate to write something like this, and that is, instead of plus C1, we write plus some sort of function of x. And of course, a function of x could also be a constant function. And over here, we could write g of y instead of C2 because there could have been any function of y. There's nothing special about the letters h and g here. We're just saying any old function of x, any old function of y. We can't say f, and we can't say f because we generally already used f to name the integrand function. So we usually use some other letter. So give it a go. Try to do a couple here examples of partial integrals and see how you do. And then let's try another one. All right, so, and then last but not least, there is just one sort of prerequisite example for this section, a little bit more challenging for a partial integral. Give it a go. It's a partial integral we will run into later on in this section, so try that. And that's it for this this video. Again, we will finish up the packet in class together. Thank you.